Welcome everyone to my video on the topic about the development of the periodic table of elements. Today we have a distinguished panel of experts who have played crucial roles in shaping our understanding in the elements. And so, joining us today we have Antonio Lavoisier, often referred to as father of modern chemistry. Next, we have Johann Wolfgang Brenner, known for his discovery of the triads. Then we have John Newlands, famous for his law of octaves, followed by Clotilde Meyer, who contributed significantly to the development of the periodic tables. Dmitri Mendeleev, the creator of the periodic table as we know it today. And finally, Henry Moseley, who refined the periodic table using X-ray spectroscopy. Our journey into the development of the periodic table begins with none other than Antonio Lavoisier, often hailed as the father of modern chemistry. Mr. Lavoisier, could you please share with our young viewers your significant contributions to the field of chemistry and how they laid the groundwork for our understanding of the elements?
Thank you for the introduction, and it's a pleasure to be here today. My work primarily focused on the law of conservation of mass, which states that matter cannot be created or destroyed in a chemical reaction, only transformed. This principle was fundamental in shaping modern chemistry. Additionally, I conducted extensive experiments on combustion and identified oxygen as a key component in the process. Furthermore, I proposed the name oxygen for this vital element and recognized hydrogen as a distinct element as well. These discoveries laid the foundation for later advancements in understanding chemical reactions and the composition of matter.
Your contributions indeed set the stage for the development of modern chemistry. How do you think your work paved the way of the eventual organization of the elements into the periodic table?
My research on the composition of compounds and the identification of elements played a crucial role in establishing the groundwork for the periodic table. By understanding the elemental composition of compounds and the behavior of individual elements, scientists were able to discern patterns and relationships among them. This paved the way for later chemists to organize the elements systematically, leading to the creation of the periodic table.
Thank you, Mr. Lavoisier, for your invaluable insights into the early stage of chemistry's development. Your work continues to inspire generations of chemists worldwide. Now, let's delve into the contribution of Johann Wolfgang Brenner, whose discovery of the triads was significant milestones in the development of the periodic table. Mr. Brenner, could you please enlighten our audience about your groundbreaking concepts of triads and its relevance to the periodic table?
Thank you for having me. It's a pleasure to be part of this discussion. The concept of triads, which I introduced in the early 19th century, was based on the observation of similarities among certain groups of 3 elements. I noticed that when I arranged elements with similar chemical properties in groups of 3, the atomic mass of the middle element was approximately the average of the other 2. This led me to propose the idea of triads, where the properties of the middle element were intermediate between the other 2.
That's fascinating. Could you provide an example of one of these triads and how it's contributed to our understanding of chemical relationship?
Certainly. One of the most well-known triads is the lithium, sodium, and potassium triad. I observed that lithium, with an atomic mass of around 7, sodium with an atomic mass of around 23, and potassium with an atomic mass of around 39, exhibited similar chemical properties. Additionally, the atomic mass of sodium falls approximately midway between lithium and potassium. This pattern of properties among the triad members provided early evidence of periodicity in the chemical elements, laying the groundwork for later developments in the periodic table.
Your discovery of triads undoubtedly provide valuable insights into the relationships among the elements. Thank you, Mr. Brenner, for sharing your pioneering work with us today. Now, let's shift our focus to John Newlands, whose law of octaves was another significant step towards the development of periodic tables. Mr. Newlands, could you please explain to our viewers what your law of octaves entails and how it contributes to our understanding of the elements?
Thank you for having me here today. It's a pleasure to discuss my contributions to the field of chemistry. The law of octaves, which I proposed in 1865, was based on the observation that when the elements were arranged in order of increasing atomic mass, every eighth element exhibited similar properties to the first, much like the octaves in music. I noticed this repeating pattern among certain groups of elements, which allowed me to classify them into rows or periods. My law provided an early attempt at organizing the elements systematically, laying the groundwork for the development of the periodic table.
That's quite an innovative concept. How did the scientific community respond to your law of octaves when you first proposed it?
Initially, my law of octaves was met with skepticism from some quarters of the scientific community. Some critics dismissed it as mere coincidence or arbitrary pattern seeking. However, over time, as more elements were discovered and their properties further studied, the validity of the periodicity I observed became increasingly apparent. My law paved the way for subsequent advancements in our understanding of the periodic nature of the elements.
Thank you, Mr. Newlands, for your enlightening explanation of the law of octaves and its significance in the development of the periodic table. Your pioneering work has undoubtedly left a lasting impact on the field of chemistry. Let's continue our exploration of the development of periodic table with Lothar Meyer, whose contributions were crucial in laying down the foundation for our modern understanding. Mr. Meyer, could you please share with our audience your insights into the periodic table of atomic volumes and how it contributes to the organization of the elements?
Thank you for having me today. It's a pleasure to discuss my work in the field of chemistry. In the late 19th century, I conducted extensive research on the relationship between atomic volume and atomic weight of the elements. I observed that when the elements were plotted according to their atomic volumes against their atomic weights, they exhibited periodic patterns. Specifically, elements with similar chemical properties tended to occupy similar positions on the graph, forming what we now recognize as groups or families. This graphical representation of atomic volumes provided a visual demonstration of the periodicity of the elements and helped pave the way for the development of the periodic table.
That's truly fascinating. Could you provide an example of how a graphical representation of atomic volumes elucidates the periodic table relationship among the elements?
Certainly. One notable example is the alkali metals, such as lithium, sodium, and potassium. When plotted on a graph according to their atomic volumes and atomic weights, these elements exhibited a clear periodic pattern. The atomic volumes of these elements increased systematically as their atomic weights increased, with each successive element in the group occupying a position similar to the one before it. This pattern of periodicity provided valuable insights into the underlying structure of the elements and their relationships, contributing significantly to the development of the periodic table.
Thank you, Mr. Meyer, for your elucidating explanation of the periodic table of atomic volumes and its roles in shaping our understanding of the elements. Your work has undoubtedly left an indelible mark on the field of chemistry. Now, let's delve into the pivotal contribution of Dmitry Mendeleev, the renowned chemist whose creation of the periodic table revolutionized our understanding of the elements. Mr. Mendeleev, Could you please share with our audience the process behind the development of your periodic table and its significance in the history of chemistry?
Thank you for the introduction. It's a pleasure to be here today to discuss my work. In the late 19th century, I set out to organize the known elements in a systematic manner that would reveal their underlying patterns and relationships. Despite the challenges posed by incomplete knowledge of the elements at the time, I recognized that there were recurring patterns in their properties and atomic masses. Using this insight, I arranged the elements in order of increasing atomic mass and observed that elements with similar properties tended to recur at regular intervals. This led to the creation of the periodic table, with elements grouped into periods and families based on their properties and atomic masses.
Your creation of the periodic table was undoubtedly a monumental achievement. Could you elaborate on the significance of your periodic law and how it influenced our understanding of the elements?
Certainly. The periodic law, which I proposed alongside the periodic table, states that the properties of the elements are a periodic function of their atomic masses. This law provided a unifying principle that explained the observed patterns and periodicity among the elements. By organizing the elements according to their atomic masses and properties, the periodic table not only facilitated the prediction of the properties of undiscovered elements, but also revealed gaps in the table where new elements were yet to be discovered. This predictive power and systematic organization laid the groundwork for further advancements in chemistry and our understanding of the elements.
Your contribution to the field of chemistry is awesome, Mr. Middleleaf. Have a profound and lasting impact. Thank you for your sharing your insights into the creation of the periodic table and the periodic law with us today. Now, let's turn our attention to Henry Moseley, whose pioneering work in X-ray spectroscopy defined the periodic table and revolutionized our understanding of atomic structure. Mr. Moseley, could you please explain to our viewers how your experiments with X-rays contribute to the modern periodic table?
Thank you for having me. It's a pleasure to be here to discuss my research. In the early 20th century, I conducted experiments using X-ray spectroscopy to investigate the atomic structure of the elements. I discovered that each element emitted characteristic X-ray frequencies that were directly related to the element's atomic number rather than its atomic mass. This led me to propose that the atomic number, which represents the number of protons in an atom's nucleus, is the fundamental property that determines an element. By rearranging the elements on the periodic table based on their atomic numbers, rather than their atomic masses, I was able to resolve inconsistencies and anomalies in the previous ordering of the elements.
Your discovery of the relationship between X-ray frequency and the atomic number was truly groundbreaking. How did this refinement of the periodic table impact our understanding of the elements?
By organizing the elements based on their atomic numbers, rather than their atomic masses, the periodic table became more accurate and predictive. Elements were now arranged in order of increasing atomic number, with each successive element representing an additional proton in the nucleus. This reordering clarified the periodic trends observed among the elements and provided a more rational basis for understanding their properties and behaviors. Additionally, it laid the foundation for the development of quantum mechanics and our modern understanding of atomic structure.
Your contributions, Mr. Moseley, have undoubtedly reshaped our understanding of the elements and their relationships. Thank you for sharing your insights into the refinement of the periodic table through X-ray spectroscopy. In conclusion, the history of the periodic table is a testament to human curiosity and ingenuity. From its humble beginnings to its modern-day application, it continues to inspire awe and wonder in scientists and students alike. As we gaze upon this elegant arrangement of elements, let us remember the countless minds that have contributed to our understanding of the universe, and let us continue to explore, discover and unlock the secrets of the elements.